So again, this is the amount of energy it took to assemble this system. What would happen if we release them? What would be the velocity of one of the particles after they've been traveling for a very long time? If we were to release all these particles, they would have clearly experienced a force, but the force that they would experience wouldn't be constant the whole time. It'd be constantly changing. But we know how much energy is there. Once we understand that we know the energy, if there's nothing else to take that energy away, all of that energy would have to be transferred into kinetic energy. Now, there are 4 particles, all of equal mass. That was the hint. That was in there, right? The idea that inertia still plays a role in this. We can't get away from that. So your mechanics class and the stuff that you learned last year, that still plays a role here. And there are 4 particles, which means we would have 4 times 1/2 mv squared. And yes, this is exactly how you would figure out how fast an individual particle would be traveling. If we know how much energy the particle has, then we can determine quite straightforward, like how fast they would be going. We just set those 2 things equal to each other and solve for v. It's important to understand, though, I was careful about the circumstance, right? Would it be the same if I just released 1 particle? So that's an important question. How would we do this problem differently if we were only talking about 1 particle? So let's say I'm going to release just, say, this one down here. How would this problem be different? Think on it. Talk to each other. All right, that should be enough time. Let's hear from some other table. How would this problem be different if we were only going to release 1 particle? Owen? I'm not sure I can hear you because you're farther away now and you're not speaking up or enunciating.
You find the energy or the influence that the 3 other particles have on it, the status or total energy?
Sure. Find the potential right here, right? Find the potential from the other 3 particles, which we really did already, right? It's buried in here, isn't it? We would take 2 of those and 1 of those. And that would be the total electric potential energy that would be associated with placing this particle right here. That's how much energy would be released when I just let that 1 particle go. That means there's less energy for the rest of them later, but that velocity now would be based on how much potential energy that 1 particle had. So, of course, I wouldn't have 4 of them. You have to get rid of that 4 and just do 1. You follow this a little bit? There's a couple ways this problem is framed. This is one of them. It's not a particularly hard question, but you do have to have the electric potential or the potential energy first. There's been problems like this for years. Another one is if I have a particle that's very far away, and I want to launch it with a velocity that will allow it to come to rest at the center of the square. Well, how fast would you have to launch it? It's the same problem, isn't it? You would have to find out what the electric potential is at the center of the square. And then from there, figure out how much energy this particle would have. Say this particle is particle Q. Set that equal to the kinetic energy, and you have to fire it with that much energy so that it would come to rest perfectly at the center of the square, right? Converting all the kinetic energy into potential energy. You see how that's the same question, right? Are you sure? Make sure you're paying attention. I'm telling you the same question every time. If you're not seeing it that way, then we need to explore it. So do me a favor, since the look on your face suggests there's problems. I have particle of charge Q, mass m. I want to launch it with a velocity that will land the particle at the center of this Q. With what velocity would I have to launch my particle? If you don't know where to start, find the electric potential at the center of the cube. I'm going to call on one of you for it. You should be able to do it with what we did yesterday. In fact, this one is super easy compared to yesterday. Anybody who's written this down, you're doing too much work. Don't need it. Don't need it. Yes, I get that the electric field is 0 at the center. You don't need any of that. I asked you to find the electric potential at the center. There are 4 charged particles in a square, and you already know the electric potential due to a single charge. You need to find out where the center of the square is, and then find the electric potential from one of them, right? They're all going to contribute the same amount of potential because they're all the same distance away from the center. You don't need to do this again. We've already done it once for the point charge. You don't have to do it again. I really hope that without looking, you're able to write out the expression for the electric field near a very long line of charge. This is what I'm wanting. I'm wanting these memorized. Is this what you wrote down? I really hope so. I want these in your memory. You could have used Gauss's law to find it. I don't want you to have to use Gauss's law to find it. You don't have the time. Now, if instead let's say we have a I don't know how I even want to draw this. This is how I want to draw it. Or maybe I don't. Maybe I can't do it. Maybe my drawing skills are just too pathetic. We'll try one more time. There. That'll do. That'll have to do. All right, so I have this thing. It's not a line of charge, but it's like a cylinder of solid cylinder. That's very long and has charge density. Let me get rid of this guy because it's not going to be that anymore because it's solid. So it has a charge density of rho and has a radius of A. Can you, using your advanced powers, adjust this for the electric field a distance S away where S is always greater than A? You might need to use Gauss's law here. Or you might be able to reason out what it must be. I don't know which one you're going to have to be able to do, but I'm hoping that maybe you can reason it out. But if you can't, Gauss's law goes really fast here. Right? I'd use probably a cylinder for my Gaussian surface, using all the symmetry. and that's not a well-drawn cylinder clearly, but want to make this a bit of a hurry. H for the height of my cylinder. So the Q enclosed, let's handle that first. The Q enclosed has to be equal to the charge density times the volume of the cylinder enclosed. That would have to be equal to rho times pi a squared h. That would be the Q enclosed. Any question about where any of that came from? All right. So my flux, break up my integral into three things, right? Based on the way we've done this before, because we have to make sure we cover all three sides. The top, bottom, and around the outside of the surface. Top and bottom have no flux at all. I only care about the outside surface. And so that's going to be E times the area of the outside of a cylinder, which we all know to be 2 pi s times h. I have to use s here, right? This is where the 2 came from. Have I done anything weird yet that's not already something we've done? Okay, so for all of you struggle buses out there, Q enclosed equaled epsilon naught times the flux. So the H's cancel out. All right, I have rho pi a squared h equals epsilon naught e 2 pi s h. The h wouldn't have mattered. We expected that. And then I divide out all the things to get E equals. And I'm going to write it a little weird, but just, you'll see, I think, in a minute. I'm going to have rho divided by, rho pi a squared divided by 2 pi epsilon naught s. I'm not canceling out the pi's right now. I'm doing that on purpose. The only difference between having a thick cylinder and having a line is that the line has linear charge density. That would be charge per meter, right? Coulombs per meter. I have to have an expression here where I still have coulombs per meter in the top, or else the units don't work out. The fact that it's a solid cylinder merely means that I have to deal with it. How do I convert my solid cylinder to look like a linear charge density? Well, it's going to be the charge density of that volume times the cross-sectional area. That will give you the charge per meter, assuming the cross-sectional area stays the same all the time. Now, if you didn't know that, if you couldn't come to grips with that in your head, I clearly said Gauss' law is not hard to do. Was that process particularly tough? There's a reason why I'm doing all this, and it's not because I want you to struggle here. If you have to use Gauss' law, then do Gauss' law real quick. The reason I want to talk about this is because you have a problem in your homework that's impossible. And I want you to understand why it's impossible. Okay? So we have adjusted our expression, and I've kind of written all over this. So I'm going to move all that garbage off to the other side unless you need to see it to write some of it down. Are we all okay with that? I want to get rid of this and write in what we just did. That if this was a very long cylinder, and again, I want to say that it is, that if I am a distance s away and it has charge density rho, then the electric field is rho pi a squared over 2 pi epsilon naught times s, where s is my distance from the center to this point. I did not say minus S, because that would not make sense. But if that's what it sounded like, I am sorry. I want you to find the electric potential at some distance near this line of charge. And this is similar to a homework question. The problem, and there is a problem with the homework question, not that you couldn't do the homework question with this, there's a problem with actually making one of these, which is why I want to look at it this way. Now, to do this, we have to, of course, actually use this thing here. We're not going to be able to get around this. And at the same time, if we're finding the electric potential, we have to start someplace far enough away. Right, where the electric field is 0, that'd be infinitely far away. Now, S represents this specific spot. So I'm going to replace, in this calculation for electric field, S with something that just represents the perpendicular distance away from the wire. How about R? Is that okay? Since R is already part of my integral. So I will rewrite this from infinity to S, rho pi a squared over 2 pi epsilon naught times 1 over r dr. The dot product, I think we can handle that okay. Wouldn't the dot product be cosine of 0? Because the electric field points away from the wire and r points away from the wire. All of this is a constant, right? Every bit of it. It will pass seamlessly through the integral. That's going to happen a lot for these problems, which is why you only have to know a couple antiderivatives to be successful in this class. So, as hard as the math might be, knowing that you only need a couple of antiderivatives should simplify it a little bit. The problem is this is one of the ones you need to know, and it's not an easy one, is it? Because you can't use the polynomial rule here. So how many of you know what the antiderivative of the inverse is? So anybody who's completed a course in calculus should, because it's one of the basics. If you haven't, then you need to know it now. So this, you can't use the polynomial rule because you'll be dividing by 0 if you use the polynomial rule. That's why the polynomial rule won't work here. The antiderivative of the inverse is the natural log. So when we take this antiderivative, we get the natural log of r. You'll learn why that is in your calculus class. And please, stop telling your calculus teacher, can't we just do this because it's so much easier, when they're making you do it the hard way. So all we did is we took our infinity and made it a little different to deal with the actual tenets of the problem.